Alright, in this video, I will discuss the analog to digital converter. Um, I will not discuss the programming because the programming will cover by the other video. So it's just an overview of the ADC. Uh, so first of all, let's say we have the analog signal that can swing from minimum, say call it as negative Vref up to maximum of positive Vref, and we feed to the ADC, right? We feed to ADC, and then the output, the corresponding digital voltage will be some looks as shown, right? Which actually it is in the form of the binary code. For example, here we have B naught. Say we n we have say 8 bit, 8 bit 8 bit what's 8 bit ADC, right? So n is equal to 8. So the maximum, the digital voltage is 2 power of n minus 1, which is equal to 2.5. So that's correspond to Bref positive. If the input is at Bref negative, and then the output will be 0 at 0. Assume that the voltage at the middle of between minus Bref and up to middle of Bref negative to Bref positive. Assume say Bref negative is at 0 and then Bref positive at 5 volt. So the middle is at 2.5 volt. So the output is half of the the voltage, which is equal to 2 power of 7 minus 1, which is equal to 127. 127. So you can calculate it later. We have I will show you the formula how to calculate that, the corresponding digital voltage. But before that, we see how the continuous signal, continuous time signal, as we call it, means the voltage is continuous and the time also continuous. So that signal is fed to the sampler. The sampler just a switch, a switch that we sample the signal, say at the fixed interval. So from that, then we have the discrete time signal, because of the fixed time voltage. The fixed time interval. So from that, then we feed the signal into the holding circuit, which is, the idea is only the capacitor, right? So, and then we feed to the quantizer that will quantize the signal to the we can see that to the nearest, corresponding, corresponding I say digital voltage or code, right? Then from that, then we have the discrete amplitude signal, and feed to the encoder. Then we have the output of digital signal in binary form. So the signal can be I express it in hexa, 0x23, for example, 0x42, 0x51, 0x63. That's if we read the signal at a discrete time or at a fixed interval of time. But it can be just in need when necessary, when required, then we read the signal, right? So the signal will be fed to the holding circuit sample for sample, then we call it as the simple and whole circuit, actually that one, feed to the quantizer, and then form it into the binary signal. Okay. So there are a lot of types that ADC available. The first ones maybe the flash ADC, very fast with high speed conversion but expensive and consume more power, often used in high speed application like digital oscilloscope. Okay, this is a flash ADC. We will see the circuit later on. That's for just for what to understand what is a flash ADC. Flash, right? Just like a flash, it works very fast. Second one, we have a successive approximation register (SAR) that is, widely used in the microcontroller because what's it's balance speeds and power consumption well, and then it is widely used in application with medium to high resolution and speed, such as data acquisition system, very simple one. Then we have a sigma delta provide high resolution accuracy but slower conversion rate. Dual slope ADC good noise amenity. This one's actually the 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 block diagram is a bit different to the successive approximations. It is used some sort like, actually, it look like charging the capacitor, and then and then what and then taking the time taken for the charging and discharging of that the voltage across the capacitor. Okay, I don't want to talk about others because as long as you understand that there are a lot of available converters, and in microcontroller the first one, flash ADC and successive approximation register, are widely used. Others, mm, sometimes used. Okay, and then the terminologies that common: resolution, the number of bits used to represent the digital output. Remember, when I talk about this, I say that assume that we have 8 bit, right? 8 bit. So it means that the output will be from 0 up to 255, right? From 0 up to 55. If we have 10 bit, it means that the output will be from 0 up to 1023, right? Or 1023. So it means that, example for 8 bit, that means it can be 0 0 0 0 0 0, right? Up to 11111111, which is 255. All right. And then sampling rate, the speed at which the ADC sample, right, the input signal. For the STM, it can work up to 2 mega sample per second. Mega sample per second. When 2 meg sample in 1 second. And quantization is means the way we map the input analog values to discrete digital values, that quantizations. And then from that we have quantization error. So the difference between the actual analog value and the quantized digital value. So we can see here later, right? You can see here later. I think it's right. Okay, if you see here, so this one we have error here, right? We have a bit error here. See? So this one will be assumed as 0100 because it's close to, but this one is still 0100. It depends on, right? Depends on the ADC, but for the normally it is assumed as 0100. So this one and this one are about the same. So here we can see that we have an error. Same with this, right? It will be 0100, but this one will be 0111. This one will be 0111, and then this one, it is, yeah, close to 1000. So it's 100. This one close to 100. So all these three, 1 to 3, is equal to 1000, eh? The amplitude value, right? Amplitude value. All right. From that, then we have the okay. So next we have the full scale range. The full scale range mean the maximum input, the maximum input that uh the maximum range that you can fit to your 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 ADC. For example, if we have 0 up to 3.3 volt, that means the minimum voltage is 0, and the maximum is 3.3. More than that, we will assume as 3.3. More less than 0, we will assume to 0. Less than that, more than then maybe your ADC will burn out, right? Maybe your ADC will burn out. So the full scale range is you know for example, if we have negative 2.5 up to 2.5, then we have 5 volt. But when we are working with the in practical, we always works at maximum at half full scale range. That means if we can work at 5 watt, then we will work at 2.5 watts, right? Because of uh, in the real application, maybe we have some sort like uh, swell, swell of the signal, right? Or we have the noise, right? Noise that more than than the full scale range. Conversion time, the time that ADC takes to convert an analog signal to digital output. This is when we talk about about the flash converter later. When we see it, it's very fast. We can ignore the time. But when we talk about the successive approximations that based on the counter, so it takes time. The higher the bit, the higher it takes to convert the signal. Settling time, the time taken for this output to stabilize after change in the input signal. So that is a meter of our sample and hall. And Nyquist rate, the minimum sampling rate required to avoid aliasing. This is twice the higher frequency of the input signal. For example, if we have a signal at 1 hertz, I mean the maximum frequency at 1 hertz, then the sampling should be more than 2 hertz, more than 2 hertz. So aliasing is the effect of under sampling, which cause high frequency signal to appear at lower frequency in the output. So that's we call aliasing. We call aliasing. And then oversampling. So in signal processing, normally we will sample at the higher rates, right? At the higher rates. For example, if we assume that we have a signal of 1 kilohertz, that is the maximum frequency. Then we filter. Assume we filter it at say um, at 1 dB, 1 decade above, so at 10 kilohertz, then we sample at 20 kilohertz. So, and then, so because we sample is 20 kilohertz, that means we sample 20 times the signal, right? From the signal. So, say we only want 10 signal per sample, then we divide it or average it by 2, right? Average it by 2. So that is oversampling. So this is the method we use in the signal processing to have better resolutions and noise, signal to noise ratio. Okay, so this is the flash ADC here. So the flash ADC is very simple. We have a quantized differential comparator. We feed the signal to it. So from that, then we form the outputs here. For example, here with the voltage more than say the point here, say the point here, say 0.1 volt, say. So the voltage is more than 0.1. See, this point is 0.2, right? So we use equal weight of resistor. We divide it. So we have 1, 2, 3, 4, 5, 6, 7. Actually, we have 7 range. 1, 2, 3, 4, 5, 6, 7. So we can divide it. Say we have 7 volt. So this one weight 1 volt, 2 volt, 3 volt, 4 volt, 5 volt, 6 volt, and 7 volt. Right. So more than 6. So it become 1, 1, 1, 1, 1, 1. Say we have 2 volt, 2 volt. So 1 volt, 2 volt here. So we have 1, 1, 0, 0, 0, 0. From that, then we need to have some sort like circuitry. We call it as logic encoder to encode the signal into digital output. For example, here we have 1, 1, which is in binary is 3. So we want to say it is 2 volt. 2 volt, right? 2 volt. So we can see that 0, 0, 0, 1, 0, right? 0, 0, 0, 1, 0. So when it is become say 3 volt, 1, 2, 3, right? 3 volt. So here become 1, 1, 1, 0, 0, 1, 1, 1. So 0, 0, 0, 1, 1, 1, 1. We need to convert it into 0, 0, 1, 1, which is equal to 3 in binary. Okay. All right. So that is the flash. So we can see here just a matter of the signal, uh, just a matter of the time taken to compare the signal and the input signal with the different voltage and then feed to the logic encoder. The propagation delay very small. See the propagation delay of 12 microsecond. So it's very fast. Right? So that's why we call it as flash ADC. But however, it needs a lot of comparator. So by increasing the number of comparator, we have a higher resolution, but the cost is increased. That's why this flash ADC is rarely used, except in the case that we need the very high, what, uh, very good, right? Very good ADC outputs, right? Next, we have the successive approximations. Right? This is the basic successive approximations. Uh, so here we have a simple and Hall signal circuitry. We feed the analog here. Assume first we apply the start signal. When we apply the start signal, so we reset the up counter. So the up counter becomes 0 0 0 0 0. So when we feed 0 0 0 to DAC, DAC, digital to analog converter, so this point becomes 0. So when we convert with any voltage that greater than 0, so this one become 1. So once, and then when the output here 1, that means we allow the gates here and gate to pass the clock to the up counter. So the counter will increase, increase and increase and increase and increase until the output of DAC is approximately succeed the input signal here. So the output here becomes 0. So when the output here becomes 0, the output here to change from to 0, right? To 0. So from here, then we can see, we can have the control logic that detect the changes of these, right? The changes of this. This one should be here. I made a mistake. This one should be here. So the changes from low to high of the comparator detected by the control logic, and then it will generate the interrupt. So the interrupt signal means the end of conversions, end of conversion or stop conversion or end of conversion, EOC. EOC. From that, then we can read the data. But actually, the data is not here, not available here, because we have a latch, transparent latch here. So to make it available at the data line, so we need to apply a clock, maybe for the latch. So the data, whatever data that we have at the output of, or the line, the bus here, output of the counter will be feed to the data. Then from that we can read it. Okay, so that is the successive approximation uh, ADC. So from here we can see that the more time, the greater the voltage here, the more time takes for the counter to count up, then it will take the conversion times more, right? More conversion time. Okay, then this is the input and output relationship of the converter or ADC, whatever it is. So from here, I show you we have a 3 point, which is A, B, and C, which is, right, the coordinate of A is equal to x1, comma y1, and then B equal to x2, y2, and then C, x3, y3. All right. So the x-axis represent uh, the input, right? The inputs. So it can swing from minimum BREF negative to maximum BREF positive. Whenever it is at BREF negative, you can see that at y-axis, it corresponds here, the voltage here becomes 0. The corresponding voltage is 0. When the voltage swing up to BREF positive, then you can see that the output is 2 power of n minus 1. Right. The digital is. So here we have 3 points. So we can use the interpolation technique, interpolates. So we can write down the formula, which is y2 equal to y1 plus x2 minus x1 multiply with y3 minus y1 and then x3 minus x1. Oh, that all the coordinate that I took from the the graph, right? So now we change. What is y2? Y2 is actually, if you see here, y2 here, right? is a V digital, right? Y2 is a V digital, the output. And then Y1 is 0 here, right? 0. And then replace X2. X2 is the V analog, the input, right? X2 is V analog, and then X1 is the Bref negative, and then we have Y3. So what is Y3? Y3 is 2 power of n minus 1. And then what is Y1? Y1 is the Y1 is 0, right? 0. And then what is X3? X3 is a Bref positive. And then what is X1? X1 is Bref negative. So from that we can write down the formula equal, so Vdix equal to 0 plus V analog minus Bref negative multiply with 2 power of n minus 1 minus 0 over Bref positive minus Bref negative. And then from that, then we can rewrite it, okay, taking out 0 and so on. So we have V digital equal to V analog minus Vref, okay, multiply with 1 over SR. What is SR? SR is a step resolution. Okay, step resolution, which is equal to Vref positive minus Vref negative over 2 power of n minus 1. Step resolution is the the smallest step that it takes for the analog signal to be converted into into one bit. That is step resolution. So we can see that from the formula, Bref positive minus Vref negative over 2 power of n minus 1. The higher the n is, the smallest the step resolution, the best resolution, the better your ADC. But however, the greater size of bits, it takes more time, and of course the cost to develop it. Next we have from that also we can make use it, right? From that third equation we can rewrite V analog is equal to V digital multiply with SR, then with plus with Ref negative. So at any time you can calculate what is the V analog for that. For example here, V digital equal to V analog minus V ref. Okay, now assume that our B ref negative is negative 0, and then our SR is 1 over 2 power of SR. Assume that SR is we use 8-bit. So and then simple calculations. Let's say our B ref positive and B ref negative is 0 and 5 watt. So 5 minus 5 minus 0, 5 watt. 5 divided by 2 power of n, or 2 power of n minus 1, which is 2 power 8 minus 1, so equal to 255. So 5 divided 255 is about 0.01957, about 19.57, I think, milliwatt, right? Milliwatt. That is one step resolution. So if given for you, let's say your B detail, your rate at the time is 100. So 100 multiply with point SR, multiply with SR plus V ref negative, or V ref negative 0. So from that you can calculate that B digital is 19.57 milliwatt multiply with SR 100. So you got about 1.9 watt, right? 1.9 watt. So V digital of 100 is correspond to about 1.9 volt or analog voltage, right? So this is will be used in our code later. So what we get from our ADC is V digital. So by multiplying with our SR step resolution and plus with VRF negative, whatever it is, it can be 0 or can be negative or can be positive, it depends on. Then we can get V analog. So if we have the relationship of the V analog to the certain quantities, such temperature or so what, then we can make use of it to produce the temperature, for example, the reading of that temperature, for example. So that's all about the analog to digital conversions. And now I will talk about the STM ADC 32 ADC block diagrams. So this is a basic block diagram of it. So it has number of channel n0, a in1, analog input 1 up to x. Then it depends on the family or use. Some it has a number of ADC. Right? Normally we have one. For example, STM32F401, we have only one channel. Sorry, one ADC. Right? One ADC. But we have number of channel. For example, if we have four others, right? Maybe we have two. For example, we have, if I'm not mistaken, 303. STM32F303. We have I can say the ADC. So we can convert one channel send to ADC, first ADC, another channel we send to another channel, right? So we have a selector here or analog multiplexer here, okay? So here we have ADC CSR that is being used to select which analog channel that we going to read. And then from here we have VREF, V analog reference, VSS, and so on. And then inside here we have a successive approximation block and sample and hold circuit. So feed the signal to sample and hold, and then feed to the SR, and then we got the result. The result in the ADC DRH and ADC DRL. What is this? Data register high, DRL data register low, right? So you have the outputs there, so we can make use of it. So in general, the ADC, the output of ADC is a 16 bit, right? But it depend on, okay, uh, the what the how many bits that you are using. We can select it. Later we can select it. We can select how many bits we're going to use. Okay, in the STM actually, we are using the what we call as the advanced SAR. Advanced SAR. So what is advanced SAR actually? Advanced SAR here is like this. Okay, now we have each time we feed a signal, then we read. We start. So we reset the counter. But this time no, we have another block that we check the label of the input signal to the nearest to the nearest to the nearest code. For example, here we have, say, the input is 1.1. So 1.1 is nearer to 1, right? So we feed the counter with the value of 1 baud. I mean the correspond counter, the bit or a code, right, or binary code that correspond to 1 baud. So as for example, for the 8-bit, we have 102. Remember, we have 5 baud here before. Our state resolution is 19.557. So 1 divided by 100. Kalau 1, if 1, that mean our voltage, our number here should be in 8-bit should be 51, right? 51 inside it. But because it is 1.01, say it is 1.5, more than 1.5, less than 2 volt. So we fit here about the correspond binary number that equal to 1.5. So 1.5 divided by 5, so we got about 76. About 76. So 76 inside here. So when we click start, so over here we already preload with that 76, and then say it is about 1.6. So it will the voltage here is about 1.5, here 1.6. So it takes about 0.1 volt to up the counter. So it takes lesser time. So with this advanced SAR, actually we can improve the speed of the SAR. So the ADC in the not all, some use flash, but expensive. Not but in general, the STM32 use the advanced, what we call advanced successive approximations ADC. Okay, and last, sampling time. What is sampling time? The ADC sample the input voltage for a number of ADC clock cycle that can be modified using SMP bits. Eh? 2 0. That means 0, 1, and 2. Eh? In the ADC SMPR, sample period, right? Register. Each channel can be sampled with a different sampling time. So we can set the sampling time, right? Later, you can see in the video how I configure it. Sampling time or cycle, or something called sampling mode, can be calculated as below. So time constant typical for the STM32 is 5 microsecond. And then ADC frequency is the frequency of ADC. So sampling time cycle must be greater or equal to time constant typical multiply with ADC frequency. Right. So for example here, say calculate the sampling time for the ADC by assuming that the typical time constant is 5 microsecond and ADC clock is obtained from the APB2, which is at 24 megahertz. So sampling time cycle greater than 5 microsecond multiply with 24 megahertz. So from here we have a sampling time or cycle greater than 120 cycle. Okay, I will not talk about the programming, but I will just show you where to set it. So assume here we have greater than 120 cycle. So if you look at here, ADC in polling mode, right? So we can set the clock per cycle, resolution, right? Data alignment, right? Scan mode and so on. And then the most important here is the sampling time. So you can check the sampling time that greater than this one, number 11, more than 120 cycle for that problem. So remember, you should know what is the operating frequency that you are working with and where your ADC is being attached to. For example, here the ADC is attached to APB2. That's why we calculate it based on the APB2. Maybe your ADC is connected to APB1. For example, if we have two ADC, one ADC at APB2 and the other one is APB1, so you need to know what is the frequency of APB2 and APB1. That's all for now for today. See you when I see you. Bye bye.